So yeah, you're good to go.
Perfect. Then, so firstly, a huge thanks to the organizers for putting this nice conference together, especially in its virtual format, and for giving me the opportunity to present this work today. And also many thanks to all the participants joining today, especially if you're based in the UK. It has been a very lovely and sunny day. So many thanks for kind of making it to this session. So today I want to be talking about multi-horizon forecasting for limit order books and limit order book data. And this is joint work done with a postdoc of us here, Zihao Zhang at the Oxford Mann Institute, and I will provide you with a reference later in the talk. So as I mentioned, this work is done at was done at the Oxford Mann Institute, and I just wanted to give one slide, just a few words to introduce the Oxford Mann Institute for those of you who haven't known it. So it's quite interesting. It's a collaboration between the University of Oxford and Mann Group, and has now been around for nearly 14 years. And it's an academic research institution which is funded by Mann Group, the hedge fund. And I think what is quite exciting about this institute is that it's also co-located with some of the research labs for Mann, which are just in the same building, actually just across the hallway. There's a Mann research lab, and that obviously makes for some very good interactions, and also means that our research is at least kind of relevant also to practitioners, which is something very important to us. So our focus here is mainly in machine learning for quantitative finance and alternative investments. So that said, let me get to the outline of the talk. So I will give a very brief motivation on the techniques we use, in particular the deep learning techniques. Then I will speak a little bit about markets at the most granular level. In particular, I will give a short introduction to limit order book data. That will be very brief, just for the few of you who might not know the concepts. And for those who do, I will keep it brief, so I won't take too much time away with that. And then I'll be speaking about kind of our new models, those multi-horizon forecasting models for short-term price moves, and how is that constructed, as well as the results, before kind of commenting a little bit on some applications where could those models be used in industry, and some conclusions of everything we have discussed so far. So off to the motivation. So I think all of us have seen the rise of deep learning. It has been immensely successful in many areas, such as image recognition, as well as natural language processing. Those are the areas which really have seen tremendous successes with novel techniques, especially some of the very modern ones. Many of you might have heard of models such as GPT-3, developed by OpenAI, which is a very sophisticated and complex natural language processing model. And those plots on the right, those are some nice plots produced by GraphCore of some hardware graphs, which really just should kind of visualize to you the complexity of those models. So those models have been getting more sophisticated, but also more complex. And the big question is, can we kind of use those and employ those in finance? And obviously there are a lot of obstacles. Finance data has more issues with non-stationarity, signal to noise is much lower, and that often kind of creates difficulty in applying some of the more complex models. But particularly the usage of some techniques from image recognition and language processing could be quite interesting. And we will see some techniques from natural language processing and from machine translation being applied in this talk. And by this, I don't mean the naive approaches. I don't mean to kind of look at images of kind of screenshots of some price series. And I'm actually not planning to look at kind of news data or natural language processing applied to natural language data, but more about utilizing those techniques in the context of limit order book data. And obviously, as those techniques are very hungry, it's really good to go to the kind of most fine-grained level of the data. We really want to be looking at kind of high-frequency data, because there we have a lot of data and we can really utilize those techniques. For daily data, it would be very difficult to be able to work with such techniques. So just a brief introduction to limit order book data. So apologies for those who know perfectly well what it is. So I think all of us are familiar with such a price time series, but one might ask, where does this price actually come from? And those of you who are familiar with limit order books know it's really just a manifestation of the supply and demand at the limit order book. So you have price on the vertical and size of orders on the horizontal, and I'm really showing orders resting at an exchange. So here I have the orders to sell. People place orders, they want to sell at a high price really, and people wanting to buy, they want to buy at a low price. Now, those orders to sell are also called the ask, and those orders to buy are also called the bid. And now, obviously, we could look the level with the lowest price of those selling, that is the best ask. And similarly, the level with the highest price of those buying, that is the best bid. And the mid price is just the midpoint between those two levels. So if you see a price at a in a time series, it's really just a manifestation of the supply and demand. It's really just this midpoint here. So if the price actually changes, what has happened is that someone must have canceled an order and maybe a level was pulled away, or someone actually crossed the spread, took liquidity, and the trade happened. And I just have an example of that as well. So here we have the limit order book. We have a trade coming in. Someone wants to sell. The person is impatient, he or she wants to cross the spread, and now the order matches with the resting order. A trade is recorded. In this case, it was a limit order, so the remainder stays on the book, and the mid price changes. So if you see a mid price, usually it's either through cancellation or through trades happening. But what's quite interesting is that in this data, beyond just the price, there's much more information. So you might argue that potentially, given there was maybe more volume on the ask, there was more kind of pressure to sell, and this is why subsequently the price moved down. So this is really where we want to apply this machine learning techniques to. So it's not just the fact that we have more data, but we also have more structure in the data that we can really make those techniques work at the end of the day. So now I'm going to talk about this new work of ours, the multi-horizon forecasting of price move from limit order book data. And here just is the reference at the bottom for those of you who want to look up the original research paper. It's available on arXiv, and it will also appear on Risk or risk.net in the October issue, so in a month's time, more or less. So the first thing we have to look is how do we encode this data? How do we take these limit order books and somewhat sticks them into our model? We have to somehow make them more amenable. And the way we do it is using this, what I call the kind of space-time picture, which is really just a sequence of limit order books. So we don't look at just one limit order book, but we look at sequences of limit order books. In this case, 100 snapshots, and usually we work in tick time. Tick time is like volume time. It's the better time. It's the usually event time. So you can think of for more liquid stocks, time ticks faster than for less liquid stocks. Maybe in opening hours of the morning, time is also running faster if more happens than, say, over lunchtime. So tick time is a very natural time, and everything here in this talk will be done in tick time. So here I take 100 limit order books and I basically arrange them in this picture here. So in this picture, each column is one limit order book, and I put the sizes on the top and the prices on the bottom. So what you see, so the top 10 rows are all the ask sizes, and the next 10 rows are the bid sizes, and the next 10 rows are the ask prices, and then the next 10 rows are the bid prices. And this is the entire picture. And on the vertical, I have 100 columns, which are the subsequent limit order books. So you might argue, and you're right with that, that for some equity names, for example, we would not need necessarily all the prices, because often those limit order books are dense. If you know the spread, we probably have enough information. This is why the bottom half of the picture moves so much in sync, because really all the prices of the levels somewhat move in sync. So there's some redundant information, but it can't hurt to do it in this way. For some other instruments, where we have very large tick sizes, this could be slightly different. It might be useful to do so. But here what you see quite interestingly in this picture, this is kind of the input data to our model. But what you see quite nicely is, I'm not sure whether you can see my mouse, is that here actually we have this color. So I haven't told you what those colors mean. So effectively what we do to also to be able to put multiple stocks into one and the same model, we normalize it. And to not have any look-ahead bias, we normalize it with a running z-score. So if something is light, it effectively means its value is higher than the recent past. And if it's darker, it means it's lower than the recent past. So it's running z-score normalized. So here you see this light color here means that effectively there was more volume on the bid than its recent past, and then it went down. And effectively, after we saw this increase of volume in the bid, we see the price moving up. So the price is lower, and then it moves up, as we see at the bottom when it gets lighter. So here we can actually see that kind of before the price moves up, we see this increase in volume. And what we really want to have is machine learning models doing pattern recognition and kind of picking up those trends. And we did some earlier work, which I actually presented at AI and Data Science and Trading 2 years ago on DeepLob, which is a model which actually utilizes techniques more from image recognition to actually kind of process those images and try to make forecasts. So today we are looking more into techniques from natural language processing and precisely machine translation algorithms here. So what we want to do is to do multi-horizon forecasts where we have as input data our kind of limit order book pictures, and those are rolling forward. So we have 100 input sequences here over time. And as output, I want to have predictions at multiple horizons. That's why it's called the multi-horizon model. So there could be at one horizon, which could be, say, 10 ticks. A second horizon could be, say, 20 ticks. And then another horizon could be up to, say, 100 ticks. And I want to make predictions, either of some future return, or, for example, in our case, we want to compare to some existing literature where they kind of effectively look at moves above and below a certain threshold. So you can classify it, is it going up, down, or neutral with regard to a certain threshold, which again is kind of normalized to adjust for varying volatility. So you have roughly equal balanced classes. And we can say, okay, I have a sequence of kind of events in the future, like 10 ticks, 20 ticks, 50 ticks, 100 ticks. And I want to know, is the market moving up, down, or neutral at those future time points? And what you can do in the first instance is just to apply supervised learning and effectively have a single horizon model. So I effectively have my input data, which are those images, and then I have one given future return or one given future label of up, down, or neutral, and I make one model which is just trained in a supervised manner to do this one thing. So this could be one model, but then I have to train a different model for the second horizon and a different model for all the other horizons. And those models could be anything, could be a linear model here, could be a more complex neural network model, feed-forward network. Those don't perform so well, but could be something like a CNN-based model, which is the one we had in DeepLob. But we have one model for each horizon. And what's important is that what I have learned in the prediction of the first horizon is not utilized for the prediction of the second horizon. You think if I make a good prediction for the first step, I ought to be able to roll it forward and make a good prediction for the second step, but it's not utilized. So the kind of case horizon is a completely new task. And to make it worse, the signal to noise ratio is higher if you go further away. So I have less chance of actually making this larger horizon work. And there's really where the multi-horizon models come in. And the inspiration is, so what we want to do here, we want to have one model which does all horizons in one go, in one model, which can then utilize the information learned for the short horizons to make predictions for the large horizon. So this is the distinction between the single horizon on the one hand and the multi-horizon models. But the question is obviously, how do we do that? And there's where we seek inspiration in machine translation. So you have all seen machine translation. You probably all use Google Translate. You put in what is the price, and you say you want it in French, and you get quel est le prix, which hopefully I pronounced correctly because I don't speak any French. But so this is really something everyone has used, but maybe not everyone is actually familiar with how those models actually work. So before we go into how we make predictions on the limit order books, I quickly wanted to revise to you how those translation algorithms work, at least in its most simple form. And again, those translation models, the more modern ones, those are deep learning models. They are effectively fitted using a lot of data, for example, obtained through Google Books, where you have translation in different languages, and you can train your models on those data. So the question is, how does that work? So the first step is really kind of read in a sentence word by word. So before that, I don't go into the details here, but you have to kind of vectorize your word. You have to convert your word into some form of vector representation, which you can feed into your model. So there are techniques to do that. I won't comment on those, but once you have done it, I basically feed in word by word, first word, second word, third word, and so on into the model. And what you do is you have a memory. So this H is the kind of memory, a hidden state, and it feeds in from the first word in the second word, which then has a memory burst of the kind of, you pass on the memory of the first word, and that feeds into the second word, and so on. So you're kind of building up this memory of the sentence as you progress. And once you've seen the whole sentence, or the model has seen the whole sentence, then you have this kind of the context vector. So this is the kind of abstract meaning of the model. So I'm just assuming you have already trained it. So we will talk in a little bit how to train it. But once you've already trained it, you read in this model, the model basically builds up this abstract meaning, which is the context vector. And then from this abstract meaning, it's now trying to infer the translation word by word. So you can have the first one where I kind of get the first French word, but now what I do, and there's really where the sequence to sequence nature comes in. I now take the kind of first prediction, I put in the context, which is the kind of abstract meaning I learned of the sentence, but I also feed in kind of the previous word and kind of the memory of everything learned up to this stage, really. So kind of when I do the prediction for the second word, I kind of have this memory, what I have seen before, really, and so on and so forth, until I have seen the whole sentence. And this is really how the machine translation works. And kind of to fit those models, you really kind of fix the input, fix the output, and you kind of force the model to kind of adjust its weight so it is able to find this kind of abstraction of this sentence. So what we want to do, we want to use the same techniques of machine translation now in the context of our limit order book data. So what we are doing here is taking those two components, and just for reference, they're also called the encoder. When I read in all the sentence, I encode it in the context vector, and then I take this context vector and now decode it into the French sentence. This is just to kind of set the vocabulary. So I'm taking this same model and I apply it to the limit order book data. So here we have, again, our limit order book snapshot. We pass it in exactly the same way as in the translation algorithm. We build up this context vector, which is kind of the state of the market, could be the imbalance or the change of imbalances. The model is now kind of forced to learn some meaningful representation of this sequence here to be able to make its prediction. And then I go step by step and make my prediction of future price moves. So this is what is known as the sequence to sequence models. And this is another technique as well, which is called attention, which is kind of somewhat similar. And I have a picture of attention here as well. So the idea is here that rather than having one context vector, it is only having access to the previous memory. So you see here, the context vector only has access to the previous memory. And so the memory effect decays away. So it's very difficult to pass on the memory from the first unit later on. It's easier to forget for these models. To make it a bit simpler for those models to remember things, especially if there's some form of, say, periodicity where maybe what was in the immediate past is not relevant, but which was further away is again relevant, then it is really important that you're able to kind of pay more attention to something which was further away. And this is exactly what this attention mechanism does. So you have those edges here, those are exactly the attention rates. So this context vector can pay attention not just to the previous memory, but to any other one. And it can learn how much attention it should pay to each of them. So this is another class of models. And those are the two models we are looking at, sequence to sequence and attention, and we are applying it to the limit order book data in the way which is kind of illustrated here in those pictures. And obviously, this is rather kind of abstract, but it's also worthwhile pointing out that we have made all the code for this research paper available on GitHub, so you're free to have a look at the code if you want to see some more details of how that's exactly done underneath the hood. But this is the basic idea. And in terms of results, so what we have, so we look at two data sets. So the first data set is the FI 2000 benchmark data set. So this is a data set which is mainly originated from the academic community, and as academics wanting to compare to existing literature, we really have to kind of utilize this data set to be able to compare how much better our model does in comparison to others. One major downside of this data set, however, is that it is very small. It's only 1 week of data from some Nordic stock exchange from 10 years ago. So it's harder to make any real life conclusions for it. This is why we also look at some more realistic data set, which is a data set from the London Stock Exchange, which I will comment on the next slide. But first on the results on the benchmark data set. So what we have here, we look at future horizons, 10 ticks, 20 ticks, 30, 50, and 100 ticks into the future. And I want to make predictions of, is the market going up, down, or neutral? So that's a form of classification task. And I can speak about accuracy for the classification task, but if the model is slightly not fully balanced, it's sometimes easier to talk about F1 score, which is effectively the harmonic mean of precision and recall. It's just some measure to say how good really this classification model is. And what we see here, if we train the model on this benchmark data set, and we have here DeepLoop, which is one of our older models, it's a single horizon model. So for DeepLoop, we have to train one model for every horizon, similarly for any other benchmark models, but DeepLoop was the best of the single horizon benchmark model we looked at. And then we have sequence to sequence at attention, which are our new multi-horizon models. So what we do here is we look at the kind of prediction accuracy, and what we see is that effectively for short horizons, the single horizon model effectively performs better because both horizons are small. It's easier for the model to be trained and make predictions, and kind of there's no advantage for the multi-horizon model because it doesn't really have any information from smaller horizons. So the single horizon model is slightly better, but the other ones compare similarly. But what we see is as we increase the horizon, eventually the single horizon model performs worse than the multi-horizon models. And generally we expect this to go down. Here it goes like slightly up, but this is probably to do with the kind of issues to do with the FI 2000 data set. So we'll see for the LSE, it's actually going down. So the main message is here that by actually utilizing the multi-horizon models, we are able to make better forecasts further in the future. So these are like 100 tick in the future. In clock time, this is still short. So we're talking about 30 seconds, 1 minute forecast, but actually it's pretty long for a kind of high frequency data world. So you're going actually 100 ticks in the future. So usually your predictions at those larger horizons won't be so good, but by utilizing those multi-horizon models, we're actually able to make predictions, better predictions, longer ahead. And you can think of it, I like to kind of give the analogy that kind of it's easier to make kind of small steps and get with some certainty of where you want to go, then kind of try to make a big leap and kind of don't really know where you end up and potentially even fall over. So it's actually better to utilize this multi-horizon models than to do single horizon. So this was the main work, and it got quite some press attention, was also covered in Bloomberg. And as I said, the main bit which is interesting for those practitioners of you is really looking at it at some more realistic data sets, the FTSE 100. So there we take 5 stocks for training, but that's already nearly 200 million observations. We have a whole year, 6 months training, 3 months cross-validation, 3 months test data set. And those are the results here. So kind of similar behavior for short horizons. Really, the single horizon model performs best, but the others are not far off. And as I increase the horizon, multi-horizon models tend to perform better in terms of F1 score. And as I mentioned, those results are all available. The paper is here and the code is also available. And one interesting thing is, I mentioned that here, I haven't put it in the figure, is that besides those 5 stocks, we also apply the idea of transfer learning, where we actually take those trained models and apply them to 20 other stocks the model has never seen before. So it's not just that we have a different test period, which is kind of a new period in time, which the model hasn't seen, but for stocks it has already seen. But we go one step further, where we take this model and we apply it to stocks the model has never seen before, and performance is similar. This has to do with the fact that the kind of features you're learning are somewhat universal, and that the data is properly normalized. All this normalization at the beginning, utilizing tick time, doing the Z-score normalization, but also on the output variables, predicting in tick time horizons, and also having a running normalization on the thresholds, that helps to be able to kind of normalize the data so it looks similar for similar stocks, and we can actually transfer those models over to different instruments. So that is for the prediction results. Now on another interesting result here. So not only did we build this new models, but we also looked at a different hardware and training it. So usually those type of machine learning models are trained on GPUs rather than CPU units, but we also experimented with IPUs, so-called intelligent processing units, which are new type of processors developed by GraphCore, which are quite interesting. They're like tiled and they have kind of local memory, so that allows them to kind of fill a gap somewhat in between the CPUs and GPUs. So they don't have to do everything in parallel like a GPU does, but they can do multiple computations in parallel, but not everything synced together. And this is particularly useful if you look at models such as the attention model. So we can actually see some quite interesting speed ups of like 5 to 10 times when compared to GPUs, which already have a speed up when compared to CPUs. So that was quite exciting for us, and also for GraphCore, because it was actually one of the first applications of this hardware in a finance context. So that was quite exciting to see that it does provide some benefits in this context. And this was in terms of the results. So now applications. So obviously in the academic work, we don't really go into application details. That is mainly for the practitioner to look at, but just to mention the main kind of application domains for such techniques are basically electronic execution and market making. Just remember that we are really making forecasts at small horizons. We're speaking about 30 seconds about this order when we make 100 tick far predictions. So it's really difficult to make standalone strategies with that, because the market is only moving so little. So if you were aggressively go into a position with such a small price move, it is difficult to make back the spread on both legs. So usually people would utilize it in market making, where you go into one leg of the trade passively, or for example in optimal execution. That's kind of illustrated here. You have an execution algorithm. It's trying to trade passively to save the spread, but then effectively, if then while you're trading passively, you could somewhat anticipate if the price is moving away for you, you could then cross the spread before it does so, and that helps you to save a spread. And obviously this is just a small savings, but you do that all the time across the whole universe. So that are small savings of pennies, but all across the board. So that ends up to quite a significant amount of savings if you think about a big investment fund such as Man, for example. So this is just to comment a little bit about the applications. But as I said, our main work is academic in nature, but I just wanted to point out the possible applications in industry. So this was really all I wanted to talk about. Just to conclude, we kind of briefly reviewed market microstructure and limit order books. We introduced the kind of the concepts between single horizon and multi-horizon forecasting models on the other hand, and we showed how sequence to sequence and attention mechanisms work, and how they originate in machine translation, and how we can use them for the multi-horizon forecasting task for limit order books. And we saw that at large horizons, those multi-horizon models outperform the kind of conventional single horizon models. And we also saw how IPUs can help us to accelerate the process of kind of training those models. And we also saw how in practice, for example, in execution, such models will find use cases. So this is really all I wanted to talk about. So thank you very much for staying with me, and I will have a look at the questions now, but please feel free to shout. Well, the first question was why one model for each horizon? Why not do multi-horizon forecasting with supervised learning? Well, we spoke about multi-horizon forecasting. This is really what the talk was about. So probably the question was asked right at the beginning of the talk, as I can see from the time. And then whether we did anything with transformers and RL. Yes, we have ongoing research in this direction, but there are also some other interesting groups like Petacon, Turiel. They wrote some paper also on multi-horizon forecasting after this came out, and they also did some interesting work on RL, and we have work as well in this direction, but nothing out right now. Yes, is there any discounting as a loss? No, there's no discounting. And the GitLab link, yes, there's a GitHub link. The GitHub link is in the PDF of the paper, is referenced there as part of the references. So if you go back in the slides in the recording, you can see the link to the archive paper, and you will find the link to the GitHub repository in there. In the GitHub link, we have all the code for the FI 2000. That's why we chose the FI 2000, also to kind of have everything open source. You can run the code, and the data is open source. You can kind of try it out on the data used here. But obviously the LSE data, that's proprietary data, so we can't share that. So, but I encourage everyone to kind of use the code and apply it to your own in-house data. Yes, there was a question I commented on this. Why does the multi-horizon prediction forecast decrease and then increase? Usually you would expect it to decrease as the horizon becomes larger, as we have seen for the LSE data set, where really the noise dominates. The other one was the FI 2000. Could be that there's some additional structure there. This data set, it isn't from the most efficient market, so this is my assumption. But obviously, there's quite some noise in there. So if you look at the scale, it is mainly an effect of noise, to my point of view. But intuitively, you would expect it to go down indeed, and that is what we have seen also in the LSE data set. Yeah, what method did you use to balance your model training data? So as I said, you could use a kind of a rolling horizon for the threshold. So you adjust the threshold such that it's equally balanced on a rolling look, like past looking basis. So effectively, say if volatility goes up and kind of now all your classes become up and down and nothing is neutral anymore, you will raise the threshold and you go down. This is done on a rolling basis. So doing it on a rolling basis and doing this normalization takes away some of the idiosyncrasies of the data. So you have kind of, it looks similar, more similar for different instruments, and that allows us to actually train it on multiple instruments at the same time, and then also do this transfer labeling. So the normalizations are quite important. That's why I spent quite some time on those. Now kind of going further here, so did you apply the same to train and test? Yes, we do it, but it's done on a rolling basis, so there's no look ahead method. So this is again about how to balance the data. Yes, it's done the same for train and test. And yes, this question we already had. Why does the prediction improve at longer horizons? That was just an artifact of the data. And yeah, why is it so different for the Nordic data set and the FTSE? And yes, why is it monotonically decreasing? Well, that's what you would expect actually. And if it gets more noisy, it decreases. It's just the FI 2000. It's just so little data, and it's 10 years ago in a Nordic stock exchange. It's nice to have a benchmark data set where academics can compare, but it's really not a good example of a kind of real life data set. So this LSE data set it's a real life example. That's the kind of size and also the kind of efficient market you want to really train those models on. It doesn't help you if it kind of performs well on a less efficient market, as you have seen, like the I mean, also accuracies, they're much higher on the on the FI 2000 data set than they are on the LSE, just because it's a more competitive market. And that's why you assume if you go further away, really the noise is kind of bringing the prediction accuracy down. That's exactly what you see. Yeah, how you deal with IPUs with the Python library. So that was actually quite easy. There wasn't much bespoke needed. And again, the code is available in the GitHub, and you can see the different changes for running it on the IPU and for running it on normal GPU. Now, kind of continuing with the questions, and yeah, organizers, please shout when we run out of time here. Yeah, I would guess that the issue is bigger using this model in real time. The latency of preparing the limit order book data would far outweigh any benefit of IPU, GPU, etc. Well, those type of models are used in real time. So there are industry participants which utilize such models. Also, obviously, a lot of time goes into the training bit, but actually at prediction time, I mean, those aren't very deep networks, and a feed-forward pass of the data through the network, that can be done very quickly. So that's not really a big issue. We haven't actually looked into benefits of IPUs in terms of latency for prediction. So the kind of speed ups I mentioned, those are just for training. It would obviously be interesting to see how that could be maybe beneficial also for kind of prediction time, and this could be something potentially interesting for some HFTs, but really, I mean, the complexity of these models isn't really an issue in terms of latency, because, well, the prediction step is very fast, really. So that's not a big issue. Those models aren't very deep. And then, have you benchmarked the multi-horizon model with a single model that predicts the average horizon? No, we didn't do that specifically, but yeah, that's maybe something interesting to look at. So, and I think this is at least the last question, which is posted here in this chat, and I see we just have 1 or 2 minutes left, so that's perfect timing. So thank you again, everyone, very much for kind of attending this talk and for posting all the interesting question. And of course, please do have a look at the paper. The link is there. Do have a look at the code. There's also a quite nice blog post by GraphCore covering our work, which is kind of gives you a summary, and then you can go into the paper for more details. And obviously, if there are any questions after the talk, please feel free to reach out via email. So thank you, everyone, for attending. Thank you.